next sections. We are going to get into some stuff that is not review, it's new today. But first, we're just going to talk about, this is section 1. I know we started this, I don't feel like wasting any time by going over it again. This is linear equations. And I guess I should say in two unknowns. Usually x and y. Hello.
Oh, sorry.
That's okay. You are.
Yes. Yes.
Okay. Okay. And the standard form you should all know is y equals mx plus b. You should know n is the slope of the line. You have 2 points in the line. You can say n is delta y over delta x, or y1 minus y2 over x1 minus x2. That's if we have a line, and we look at any section of it. Here's my delta y, here's my delta x, and this is the slope of this line. You should know that b is the y-intercept. The point where the line crosses the y-axis. It's going to be d. And you can go back and forth on this. If you have the equation, you should be able to graph a line. You should be able to answer questions like, is this point on the line? Well, if I give you, y equals 3x plus 2, and I say, is 1 comma 5 on the line, you can go, well, all right, 1, 3 plus 2 is 5, yeah. Or not, it's not. So, let's see. It's good to know that if m is greater than 0, your line is going uphill. M is less than 0. M is minus 1, going downhill. M is 0. What happens if M is 0? Yeah. That was the worst drawn horizontal line I've ever done. Now, if it happened that you had a line that was perfectly horizontal, well, delta y over delta x would be something over 0, which is undefined. You can have a line like this. Let's say this is minus 3. You can't use this form, right? But you could say x equals minus 3. Okay, so what do we do with this? Well, hopefully you all remember we have 2 of these equations as an example. Well, we know these are 2 lines. If I ask, how do they intersect? There are 3 possibilities. The most likely possibility is they're going to intersect at a point. And we'll talk about how to find that point in a second. It's also possible that these are parallel. Anyone recall how you know if they're parallel?
Same slope.
They have the same slope. That's right. we put these into our standard form and look at m, and it's the same. We know they have the same slope. We know they're parallel. It's also possible they're the same line. We wrote something and it looks different, but it's actually the same line. All the same points are on that line. You can think of that as a really parallel line. It's the same line. All right, but if we don't have parallel lines and it's not the same line, we want to find where they intersect. Any econ majors here? I never had any fun. This actually comes up for real, not just something make you do, torture you. In economics, they have this idea of you have a product and you want to know how many you're going to sell. So, how many you're going to sell, and then there's the price. And as the price gets bigger and bigger, you're generally speaking going to sell fewer of them. It's not always a straight line, but some portions it might be. And given some price, how many are the manufacturers willing to make? Well, the higher the price, the more they're willing to make. And then there's a sweet spot in the middle where the price is just where enough people will buy all of them. And that's very theoretical. The real world is much more complicated, but at least it's somewhat of an example of why you want to do this. All right, so you probably all remember, that there are two ways we can solve these equations. One way is called elimination. All right, the idea is we're going to add these or subtract these in such a way that one of the variables disappears, it gets eliminated. And in trying to do that, we might want to multiply by one of these equations by a constant, so that like the y's will, the negative and the positive y's will match up. You can add or subtract them, whichever is more convenient. You just look at it and say, what's the easiest way to do it? So in this case, this is a setup problem. You should look at this and immediately realize, I just want to add these because my negative y and my positive y are going to go away. So I just get 3x equals 12 or equals 4. Well, that's the x coordinate where these two lines meet. Once I have the x, it should be pretty easy to find the y. I can pick whichever of these makes it easiest. I think this one does, because 2x, x times 4, 2 times 4 is 8. I've got 8 on this side. Oh, that's going to tell me y is 0. Right? A good check that you haven't made a careless error is to plug this into the other equation. Well, 4 minus 0 is 4, so we're good. Okay, that's elimination. I guess I should break that up. Elimination. The other method is called substitution. Substitution has the nice feature that it isn't what we're going to use just for linear equations. We use it a lot of times when we have second degree, third degree. Any two curves described by equations, if we can substitute and eliminate a variable, we're a step closer to the solution. So when you want to do substitution, what you're looking for is something like y equals something, or x equals something. The y equals something without any y's, the x equals something without any x's. So we can, how do we do that easily here? Well, we can take this equation, we can add y to both sides, and we get x equals 4. And then we're going to take that x and substitute it in, eliminating the variable again. So let's go through that. 2 times y plus 4 plus y equals 8. And now I have an equation with just one variable. 2y plus 8 plus y equals 8. You can see where this is going. 3y plus 8 equals 8, or 3y equals 0, y equals 0. And then we can just plug y back in and find that x is. It usually, in a linear equation, it usually doesn't matter which you substitute, except that one way might be more complicated, more prone to careless error. So it's always a good idea when you see one of these problems to just think ahead a little. So let's, not just how can I solve it, but how's it going to come out with the least amount of fractions or multiplying large numbers. All right, so that's one way to solve this. The only reason I see it useful to try and solve this graphically is, first of all, to know that it can be done. Often when you're solving equations graphically by drawing equations, drawing their graphs, seeing where they intersect, you're often you're getting an approximation, which may be all you want. For some people, it's good to see it, to understand it. I think that's a good reason to do it. But in general, we're going to do it algebraically. All right, so let's, how would we solve this graphically? We want to graph both these equations. All right, I guess I can put everything down here too. So typically what we want to do is put them into standard form. So let's see if we can do that. I put y on this side and 4 on this side, and get y equals x plus 4. Here I can just subtract 2x plus 8. All right, and now practice a little graphing. The y-intercept here is 4, and the slope is, of course, 1. So that means I go over 1, I go up 1. Over 1, up 1. So it's going to look kind of like this. My drawings are not the most excellent. Okay, here we have a y-intercept of 8, which unfortunately I didn't prepare properly for, did I? Because it's off the board. Well, all right. Let's see if you can correct this mistake without too much effort. It's always nice to have graph paper for doing this. Okay. 1, 2, 3, 4. And slope 1. All right, so now I can say 8, 2, 4, 6, 8, and slope of -2. So it's going to be going down. So delta y or delta x -2. I go down 1 over 2, down 1 over 2. All right, now, if you were drawing this on paper with a nice ruler or with graph paper, you could find a point here. What did we decide it was 4, 0? What did I do wrong? Thank you. All right.
X minus 4.
All right. So you can see I have a lot of affection for graphing. All right, I'm just going to assume everyone in the class is better than me at it. If you feel otherwise, come to my office hours and we'll have some graph paper and we'll try it out. All right, there's a few more tidbits we want to know about these equations because they will come up. Those of you who love math, I'm sure there's one person in here. I'm not going to go over Kramer's rule. He says that, but I want you to know. Kramer's rule says, wouldn't it be nice if there was a formula, like a quadratic formula to solve this? And there is. And the way you do it, you say x equals, we're going to make a matrix and we're going to find its determinant. If you don't know what a matrix is, or you don't remember what a determinant is, don't worry. In the denominator, we're just going to have a, b, d, e. For x, we're going to substitute these for the x values, so cf, e, g. There you go, you have a formula. Now, to me, trying to use Kramer's rule is almost always much more effort and work. If you're a computer programmer, well, to write an algorithm that does substitution or elimination be a little tricky. This is just a formula. And it has the nice feature that if you, you happen to have three equations, I'll just say z, some coefficient. You have three equations and three unknowns, you can just apply Kramer's rule. Or four, or five. Economists sometimes have very elaborate models where they have lots of variables and they have to do it with a computer, and it's nice to know. So you can take a look in the book. It won't be on the exam. So I just wanted to make you aware it exists. Okay, so back to those little tidbits. Things you should know how to do. If you're given 2 points, like these 2 points, you should know how to come up with the equation. Well, first thing we want to do is find the slope. So that's going to be, you can do it either way. 5 minus 1 over 8 minus 2, change in y, 5 minus 1, change in x, 8 minus 2, that's 4 over 6, or 2/3. You can subtract 1 from 5, and 5 from 1 and 2 from 8, and it comes out the same. So once you have this, there are 2 directions you can go in. The direction I like, because it's easy for me to remember, is you just write out, well, y equals mx, 2/3 x plus b, and you plug one of these points in, either one, and plug in the other one as a check, and find out what b is. If you'd rather not stretch yourself that far, you can just remember we have point slope version of the line, which goes like this: y minus y1 equals m times x minus x1, where m is the slope, and x1, y1 is just any old point on the line. And or you could use a check. You could use these as a check on each other to make sure you didn't make a simple mistake. That's all, I think. And I didn't bring it. This. No, we'll make it here. Okay. Make sure you know how to find the equation of the line given 2 points, or given 1 point and a slope. Right? That's even easier. You just go right to step 2. Okay. Before I get to the second little tidbit, I have to talk about detail about the slope. You have 2 equations, and their slopes are equal. We already mentioned that they are parallel. You never look at it. What happens if 2 lines are perpendicular? Their angles, they meet at right angles, or 90-degree angles. Does anyone recall the relationship between their slopes?
Negative reciprocal.
Negative reciprocal. You want to know that. Because in this example, well, let's say I said, I want the line, but not the one that goes to these 2 points. I want it to go through this point, but I want it to be perpendicular to the line that goes through these points. Okay? What was the slope through these points? It was 2/3. So the slope I'm looking for is the negative reciprocal, which I hope you all know is -3/2. And I'm back to the same place I was with the original problem. I have a slope, I have a point, I can use point-slope form, say y minus 1 equals -3/2, the slope times x minus 2, and I'm done. Okay, I think that's everything you ever want to know about lines. Oh, well, I guess there's one more detail. Having to do with perpendicular lines. I had y equals 5. So what's the slope of that line? There's a difference between having no slope and having 0 slope. I mean, it's kind of subtle. Yeah, the slope is 0. So if I wanted a line perpendicular to this line that went through 4, well, what's the slope of this new line going to be? Negative reciprocal would be -1 over that. Doesn't really work, does it? It's undefined. So it's going to be of the form x equals, and for it to go through this point, it has to be x equals 3. So now you know everything you ever want to know about lines. Okay. Questions about lines before we move on? We're really going to take a steep turn now. Okay. Okay, the next section we're going to look at is section 2.1. It's a new chapter. And the subject is functions. So you probably know something about functions, and I don't want you to forget what you know, but I just want you to put it aside for a minute. Because you've used functions in a certain context, and I'm going to kind of take a step back and describe it in a very, very general way. So one way to think of a function is kind of a black box. I guess I should define what I mean by a black box. Black box is something where you put something in, you get something out. You don't necessarily know what the mechanism inside is. The rules for this black box are, whenever you put something in, some A or B, you always get the same thing out. How it gets out, how we compute it, or whatever we do, doesn't really matter, as long as it's always the same thing. So, for example, we could have a set A and a set B. And I'm in particular going to describe a function this way a lot. It consists of two things. It consists of a set, which is the A set right now, which we have a name for. We call it a domain. And we have a mapping. We map each element in the first set to the second set. Now, the most important rule about this is each element in the domain goes to one element over here. It can't go to two. If you ever see a diagram like this, so this is not a function. And we're going to talk about what, how to just, see what's not a function. Another way we might describe this is x goes to some function of x. Put it back. This describes the function. The B set here, you'll find in different places it'll be called the range. You're probably familiar with that. Some people will call it a codomain. Codomain. And some will say these are actually slightly different. And that's unimportant in this class. It is quite permissible for something in domain, two items in the domain to map to the same element. In fact, consider function of x equal to 0 times x. Consider the domain to be all real numbers. And what's over here in the range, just one element and 0. Right? Everything we multiply by 0 is 0. So functions can be that way. It can be very complicated, it can be very simple. You also can have a function, let's say, but the domain of this function is just the number 2. All right? That's a perfectly valid function. I want to emphasize a function consists of, even though I'll write f here, which kind of triggers the idea of function, a function needs both a mapping and a domain. You can automatically get the range because you put stuff into the function, you see what comes out, that's the range. It's very common in your previous lifetime, if you've dealt with functions, for a teacher to say, well, f of x equals 5 over x minus 1. What is the domain? And fight as I might for, real mathematics, rigor, this question makes no sense because it's not a function until it has a domain, right? Now, what the teacher is doing here is they're saying, well, given that the mapping is for every number, every real number that's plausible, what can be in the domain, right? So we start off with the real numbers, and then they want you to look at this and go, oh, well, you can't have 1, because that would be undefined. So r, but not equal to 0, not equal to 1. Sadly, Stewart follows this convention that if you ask, what's the domain of something, what they mean is, when they just give you a mapping, they want you to tell them, here's the things that you can't be in the domain. Just a little bit more about functions. The two sets that we map between don't have to be the same set or the same even type of object. You have red, green, blue, right? Nothing wrong with that. In mathematics, the idea of a function can be very general. It can map between numbers, geometric shapes, graphs, all sorts of things, functions. You can have a function which maps a function to another function. So it's a very general idea. There's one very important function that comes up a lot. Again, I'm taking here, I'm not going to tell you the domain, but if f of x equals x, that just maps whatever we start with to itself. And this has a special name. This is called the identity function. Which is not coincidentally the same name we use for 0 when we're talking about addition, the additive identity, or 1 when we're talking about multiplication, multiplicative identity. Now, often we'll use, I'll just write f of x, but I might have more than one function to describe, and there are various ways to pick something else. Common would be just advance the letter g of x, h of x. There's nothing different about these. It's what we usually use. If there was something about these functions that we could say, like f of x is x. My next function is x squared, and the next x cubed. I might call this f1, and f2, and f3. can use notation that way. All right. A little more vocabulary. If you look at, in this case, R, or let's make a function here on the reals. So f of 2 is 4. We sometimes will call a particular element of the range here the image. In other words, the image in this function of 2 is 4. The word image. Just a vocabulary term. When we're talking about functions, we sometimes use y instead of a function. Especially if we're going to be graphing on an xy plane. And we'll sometimes, where did I do that? There's y, there's x. We'll sometimes call this particular variable the independent variable, and y the dependent. You have to be thinking of this, some graph of some function that way. Where what you're saying is we pick an x and we get a y, right? So dependent and independent variables. All right, let's take a 5-minute break. Anybody has any personal questions you want to ask? Take a minute to check your emails. Those important texts. So, more about functions. How could we describe a function? One way is verbally, either auditorily or written. So, for example, I could describe a function that maps the name of my students in this class to their title. Just write that. Perfectly good way to describe a function. You could have an explicit listing or a table. You could say, here's x, here's f of x. I could say 1, 3, 2, 9, 3, 27. Now, if you look at that a bit, we'll probably figure out another way to describe that. Or you think you could, unless I wrote, 4, 0, and then you go. But this is a function. It doesn't have to follow a nice algebraic rule. See this, all these questions that come up all the time online. What's the next number in this sequence? You look at that and you go, looks like it's pi, you didn't tell me what my limitations were. Perfectly good sequence numbers. Output of a function. So, okay, you can have a table. You could use an algebraic expression. Like here's a common one we use. This is a function of something. I'm using the variable r. I don't always need to use x. And let's say pi r squared. And then you're going to go, this is the function that maps the radius of a circle to the area within it. So that's another way to describe a function. Again, I really should specify the domain here. I think it's obvious. It's got to be r greater than 0 because, I'm in a circle. We don't have circles with negative radiuses or 0 radiuses. But we could. Here's a table. If you have the wrong book, it's probably out of date because this seems to change every 6 months. How much does it cost for a first-class letter? And we have ounces. And, dollars. So less than or equal to 1, 49 cents. Greater than 1, less than or equal to 2, 70 cents. Greater than 2, less than or equal to 3, 1 cent. You kind of lose track if you buy those forever stamps. It doesn't matter. But this is another way to describe a function. It's mapping the weight of your first-class letter to how much you have to pay to get it delivered. Yeah, that's the example. There are different types of functions with respect to, how. Yes.
So with this example, for example, you can't have overlapping ounces, right? It's set at different prices, so you.
Well, okay, let's change this a little. I mean, this would be a little crazy. Oh, you add another ounce and it's cheaper. Oh, or it's also 49. That's okay.
But when, for example, at the bottom one, we can have it would be like, we can't have greater than or equal to 2, because.
Oh.
And isn't also treated like circles and functions?
Well, good example, right? So if we say 1, greater than 1, less than or equal to 2, 49. Greater than or equal to 2, less than or equal to 91. That means I'm mapping 2 ounces to 2 different values. And then it's not a function. Okay, I was trying to say something about, let's say I have this function x squared, and make a little table here. X, I think x is 1, 1, 2, 4. Well, the domain here is all real numbers, so 1.5, 2.55, say 1.1, 1.21, 1.7, that would be, I don't want to do that in my head. The values here are continuous. That is, for every number between 1 and 2, every real number, there's some number here. So I don't want to get into it because it's really a topic for calculus, but we call this continuous. Now, if on the other hand I have a function where I say, this is how many apples I can buy. Where apples are, say, $1 a piece. So I have $1, 1. $2, 2. So what if I have $1.50? They're not chopping up apples for me. It's still 1 apple. The range here is just a bunch of discrete numbers. They're not continuous like here. So you could have a continuous function. You could have a discrete function. I think CS majors are going to take a course called discrete math. It's going to talk about this. One of the things will be functions of it that have that are discrete functions. But there's a third kind of function that we're going to look at, which we do need to know about. We don't really need to know about discrete functions or continuous functions. There's a type of function we call, and I just erased it, piecewise function. So let me give you an example. Piecewise is more of a way of describing a function. Let's say I had the function f of x equals absolute value of x. Well, one way to describe that would be f of x equals x. If x is greater than or equal to 0. And it's equal to negative x is less than 0. So this is what we mean by a piecewise function, where we define it in pieces. Another example, I guess, is pretty much the stamp example. Say, how much does how much does it cost to send a letter, where x is the weight in ounces. So less than or equal to 1, I guess we said was 49 cents. Greater than 1 and less than or equal to 2 is 70 cents, and so forth. So it's just a way to describe a function. Now, if I gave you a graph of a function and it looked like this, so forth, I think, yeah, that's kind of what this is. You'd be inclined to describe it as a you might describe it as a discrete function. It actually looks just like this. We have another name for it too. We call this a stepwise function. You can think of probably a lot of stepwise functions. If you're still paying for your cell phone by the minute, right? they'll either start charging you as soon as you start talking, and then it's the same price until you get to 1 minute, and then it goes up 2 minutes. Or maybe they don't charge anything until you get to 1 minute. All right. Yet another way to describe a function is what I've done here, is to draw a graph. So I have a function square root of x. Okay, it's going to kind of look like this. This is actually a parabola kind of flipped over. You can't really describe this kind of function using, well, I erased it, but using some kind of table. You could describe some of the values on it, but you couldn't describe all of them, so you need an algebraic expression. All right. All right, so now that's the very, very general kind of idea of a function. We're going to be dealing with a more limited class. The most common one we'll deal with would be a polynomial function, which is a function described as some polynomial. Now, when you have an algebraic expression describes a function, occasionally you're given an assignment to evaluate this function. Evaluate this function at, say, 2. And then, I think you're all probably tell you something you already know. You just need to plug in that 2. And do a little math here. 20 minus 6 plus 2. 16. Okay. I guess I'm going to repeat myself here. I could have a function where I'm going to substitute the word should. I should have a function where I describe the domain. Let's just say I'm kind of channeling Stewart. But if I don't say anything about it in this course or in the homework problems, because I won't ask a question like this on an exam, I say, well, what's the domain of this function? You're just supposed to assume it's the largest domain over the real numbers you can have. So all polynomial functions can be defined over the reals. Function like x times x minus 1. This can take all reals except, of course, 0 and 1. Just have to be dividing by 0, which is undefined. If the f of x was 9 minus x squared, well, here we don't want to have any imaginary numbers. So x squared can be at most 9, which means x can be what? or -3, right? So these are kind of, call them trick questions they'll give you on homework. How do you know when a function when a number cannot be part of the domain of a function? Well, two main examples we're going to run into is if the denominator is 0, or if under root, square root, odd root, have a negative number. So, I think I've asked this question. How many of you have a calculator like this? How many of you call them? Okay. Hold it, keep them up for a second. I want to see how many go down. How many have one here today? It might be good to bring it on Tuesday, Thursday. I have a whole bunch here, and what I'd like you to do is make friends. If you don't have one, your neighbor doesn't have one, and maybe their neighbor doesn't have one, make friends. Come and borrow one.
Look, there's more.
So for the next part of today, what's left, we're going to play with the technology here a little. Now, if you do not own one of these and it's not something you want to add to your collection, let me know and you can borrow one of these so you can play with it on your own time. If you have a Windows machine, I have a program somewhere I can find that you can download and you can simulate these calculators. All the TIs work pretty much the same. You have a different brand. I don't know how to use it. You can learn how to use it. Let's see here. But I want to go over a few things that I think are generally useful. Any science you're in, these are going to be useful. Math, computer science, they'll be useful. Social sciences, they're good. You need to use statistics. They're useful. So we're going to look at that function, I guess. F of x equals square root of x. I'll just write it that way for now. Do it on my website. haven't been there, this is how you look at my notes. And first thing I want to bring to your attention is a feature of these calculators, which is, I'm going to, oh, you have one, or you're using this, which is the mode button. You press the mode button, you're going to see all sorts of options. The choice on the left is kind of default. I don't actually know a lot of these, what a lot of these do. But in particular, you'll see over here it says funk. And you have some choices. There's funk. Pole is polar. If we do polar, we might do polar graphing. We might do polar form. What's next to? Next. Par. Par, it means parameterized. We're not going to use that. We're not going to know what C is. So make sure your calculator is on funk. And then to get out of this screen, if you hit the orange button second and quit, that's over the mode, you'll go back to the regular screen. Let's see, did I jump too far? I jumped too far. When you're getting going, it might be a good idea to hit the zoom, and then either one of these, probably Z-box or standard. Later when we're looking at trig functions, you might want to click 7, because that might be handy. Try that out if you're not feeling like you don't want to do it yet. I don't know why I did this in this order. If you hit the window button, you get direct control over the axes. You know, we're going to have a graph here, and you can control the min, the max, y and x. It'll stretch the graph. And what am I trying to get to here? Oh, well, okay, so now you want to hit the Y key, and you're going to get a list of places you could put a function. Now, I'll be very honest, I haven't gone beyond putting more than one function in. It gets tricky. You can learn it, you can look up in the manual if you want to. There's a function where you say, I want to find the intersection of two functions, which I've never gotten to work. There's another way to do it, which I'll tell you about. But let's plug in some function here. What have I got here? I guess we could try what I've got here. X raised to the 5th minus 5x cubed plus 4x. And once you type that in, by the way, if you have a newer, like a TI 84 plus or something, you won't actually see that funny character. It'll actually give you superscript, but then you have to know when you're done up there, you have to I guess get the cursor key to go on and not be superscripted, which you might want to do. When you're all done plugging that in, hit the graph key. Let's see if I... You should see something like this. And you don't have one? We ran out. Can you scoot over and make friends? Has everybody got something to look at here, or hopefully? this is not the last we're going to do with this. I just want you to get used to pushing buttons. And you got something? Okay, that looks like X cubed, right? Okay. We're actually going to move on from the TI calculators. These are nice. You can bring them to class. You can bring them to exams. I'll let you use them in an exam. If, you know, this kind of puts to bed this whole idea of, well, you have to learn how to graph something. Well, if you can plug it in, you can see what the graph looks like, right? So, you know, it's not, technology has overcome our need to figure some things out on our own. Now, sometimes you'll show your graph and it's like, you can't really see the part you want. That's where these window and zoom comes in. At some point we may talk about calc and trace and other things. But you can see there's a nice feature to having this. Now, here's something that's actually much nicer, but you can't bring to class for your exam. You use it, you know, during class, not exam. If you happen to have a Mac, or maybe a Windows equivalent program, but the Mac has this really nice program called Grapher. So we're going to just type in, again, some all right, and bingo, I've got a graph. When you're doing your homework, if you want to look at what something looks like, this is really nice. You can zoom in, zoom out, and move it around. I think you can move it around. As I said, there may or may not be an equivalent Windows program, but anyone, well, before I go, I guess I want to, before I go from Grapher, I have to show you what's the coolest thing about Grapher, which we won't use in class, is 3D graphs. So here, let's say, I don't know, z equals x squared plus y cubed. Whoa! And, you know, you can kind of move around with the shape. It's a really nice program, really fun to explore. There it goes. But those of you who don't have access to Grapher, you all have the web, and you all can go to desmos.com, which itself has some nice features. Again, I'll just put in some kind of linear equation. One nice thing about Grapher is you can move your cursor over and click on some point, and it'll even tell you the approximate coordinates, and you can move in and out. These are all things that, you know, can help you with your homework, can help you understand you're dealing with some function that you're trying to figure out something. All right. So I just wanted to make you aware of all these nice technology you have at your disposal. I guess I could use this for the next thing I wanted to show. Let's see how this works. Let's take a look at x squared. You all should be fairly familiar with this graph. It's a parabola. But I want to add a little here. I'm going to put x to the fourth up. The blue line. It looks very similar, right? Most notably, you can see it's symmetric on the y-axis. Did we use the term in the previous class, an even function? Well, this is what we call an even function. That if you have some value, let's say 1, and it has some value, -1 is going to have the same value because it's symmetric. So this is a good way to, if you graph something and it's symmetric that way, you can guess it's going to be an even function. Just try one more here, x to the 6th, same idea. One thing you can gain from this is all these polynomial functions where it's just x to the n and it's are even functions. Now, in contrast, I wrote x cubed. This is a function which, instead of symmetric around the x or the y-axis, we say it's symmetric around the origin. And if you go over 1 and up 2, here it'll be over 1 and down 2. A rather simplistic odd function is just x, just a straight line. And I guess you can see that any odd number is going to have this kind of symmetry. All right. A few more things to go over with the graph. I'm just not sure if it really should squeeze this in. Yeah. There it goes. So this is just an example of graphing a piecewise function. If my function was x squared for x less than or equal to 1, and 2x plus 1 with x greater than 1. How do we go about that? Well, it might help to just graph x squared to look like this. It's going to have points 1, 1, and -1, 1. But this is only for x less than 1. So I can erase this. Again, leave a little fat dot here to indicate this point is included. And then I might want to graph this line, 2x plus 1. Well, its intercept is 1, and its slope is 2. Except I really only want this function for x greater than 1. So yeah, I'm going to put a little circle here to indicate this point is not included, and I'm just going to erase this. So again, with a piecewise function, it's not really different from graphing a regular function. You just have to be wary of what the limits for each piece of it are. The graphing calculators are not, and the the programs I showed you, the Grapher and Desmos, aren't very good at this. You can graph both of them together and copy it, and erase what you don't need. Right. Mentioned something called a stepwise function. There's actually a symbol that's useful for describing them. You don't see this very much. Two sets of square brackets. And this symbol means greatest integer less than or equal to x. So, for example, x were 1, this would be 1. This was half, that would be 0. It was 2.5, it would be 2, it's 3, it's 3. So, what does the graph of this look like? Well, from 0 to 1, it's just 0. From 1 to 2, it's going to be 1. And from 2 to 3, it's going to be 2. And you can kind of see how this is working. You also can see why we call it a stepwise function. It looks like a bunch of stairs. Right? This function can be useful for describing things like post office rates, right? I guess I should note it continues too, right? From 0 to negative, like I said, say from -1 to 0, it's -1. So okay. Have a good afternoon. We'll see you on Thursday.